Today we are beginning Unit 10 on parametric and polars, and we begin with parametrics. Polars is going to come after we do parametrics. So parametrics is motion along a curve. Back in Unit 4 we did motion on a horizontal or vertical line, which we also called rectilinear motion. With rectilinear motion, we talked about the position of the particle, and our independent variable was time, which we let t represent, and we said that if the motion of the particle was on a horizontal line, that we might use x of t. If it was on a vertical line, we might use y of t to describe the position, and s of t we used for either horizontal or vertical motion. We had velocity back in Unit 4, and velocity we said was the first derivative of the position function. However, we called the velocity was the first derivative. And we did things with velocity. We said if the velocity is positive, the particle is moving to the right if we're horizontal, or up if we're vertical. When the velocity is negative, the particle is moving to the left or down, and the particle is at rest when the velocity is 0. So to analyze left, right, up, down, we looked at a sign chart for velocity. Or if we were given the graph of velocity, we looked at where the velocity was changing from positive to negative. And we said that would be where the particle is changing from right to left or up to down, etc. And where the particle was changing from where the velocity was changing from negative to positive would be where it's changing in the other direction. We're going from the left to the right or from down to up. So we did things with velocity. We also had acceleration. Acceleration is the first derivative of velocity, which is the second derivative of our position function. And we did things with that. Speed is the absolute value of velocity. Speed is not velocity. Speed is the absolute value of velocity. Speed can never be negative. So if we were doing a sign chart for speed, we would only have pluses in here. We might have some zeros, but we would only have positives on the sign chart. Okay? And then we talked about when the particle would be speeding up and slowing down. Speeding up, which means the speed is increasing, we said was when acceleration and velocity have the same signs. The particle is slowing down when velocity and acceleration have different signs. And one more thing we talked about back then in Unit 4 was displacement. And displacement was our ending position minus our starting position every time. So what makes parametric motion different is that we are no longer on a horizontal or vertical line. We are now moving along a curve. So the particle is moving along a curve. Okay? To describe that kind of motion, we have parametric equations. Okay, x and y are both functions of t, and together they make a point on the xy axes to describe the location, the position at any time t. Okay? So for instance, let's say that we have x of t is 2 square root of t, y of t is 3t squared minus 2t. When time is 0, we can put 0 in for t in both x and y, and we get a location, a position of the particle. Okay, when time is 1, we can get another location of that particle. And when time is anything, we can get the location of the particle. So x and y together make a point on the xy axes, the coordinate system, and it describes the motion at any time t. Okay? All right. Now, on the first page of your notes packet for this unit, there is a list of formulas to know. And This might look kind of scary, but we're going to go through each of these in examples, and you'll see that they really are not that bad. I'm going to leave, our first example is going to deal with dy dx and the second derivative of y with respect to x. And, well, I'll talk about this real quickly. Dy dx is the rate of change of y with respect to x, the instant rate of change, right? This is the instant slope. This is the slope of the line tangent to that curve at any point x, y. Now, dy dx is the slope, but x and y are both functions of t. So to get dy dx, you take the derivative of y with respect to t and divide it by the derivative of x with respect to t. And you can see that even if we use just what we know about fractions, Leibniz's notation allows us to, when we're dividing by a fraction, we can multiply by the reciprocal, and it even looks like it would be dy dx, and it is. Okay? Another advantage of Leibniz's notation, it allows us to do that. Okay? The second derivative of y with respect to x is the derivative of the first derivative with respect to x. Okay? Now the only problem with that is you're taking the derivative of, so since y and x are both functions of t, dy dx is going to have t's in it. Right? So when you take this derivative with respect to x, you need to do it implicitly. And that's the only thing that makes this even remotely challenging. And it's really not too challenging. Alrighty? Okay. To get velocity, it is once again the derivative of the position. But we're going to have components of velocity because we have components of position. If we have x and y both functions of time, then of course the velocity is going to have both an x and a y coordinate. Okay? This makes it a vector. When we have two components, we get a vector. Okay? So the velocity vector is x prime, y prime in a vector. We'll talk more about vectors tomorrow. Acceleration is also a vector. It's the second derivative of position, or the first derivative of velocity. So each component is that second derivative. We're going to go through magnitude of displacement in an example tomorrow. We're going to talk about speed tomorrow and the distance traveled by the particle tomorrow. The fundamental theorem is used when we want to get the position from velocity. So if we have velocity, we can get position from it using fundamental theorem. Or if we have acceleration, we can get velocity using fundamental theorem. We're going backwards. So all of these we will talk about as we go through some examples. So let's go ahead and finally get to an example. What are we at? 8 minutes, and we're getting to an example. Okay. So let's talk about this same example that I started off with. X and y are both functions of time. Somebody's at my door. X and y are both functions of time, and in part A we want to find the slope of the line tangent to the curve in terms of t. Slope of the line tangent is dy dx. Okay? So we're finding dy dx in terms of t. So I'm going to be writing down everything that you need to show if you want to get full credit in an FRQ, you have to write these things down. So dy dx is dy dt divided by dx dt. Dy dt over dx dt. The derivative of the y divided by the derivative of the x. Another way we could have written that is y prime over x prime. They mean the same thing, so you choose which one you want to use. They mean the same thing. I'm going to start by writing it like this because I want you to see that Leibniz's notation, how that works with multiplying by the reciprocal of that denominator's fraction. Okay, so y prime of t is going to be 6t minus 2. X prime of t is going to be, so this is 2t to the 1/2 power. So I'm thinking of this as 2t to the 1/2 power. Power rule, so 1/2 times 2 is 1. And then we're going to subtract 1 from the exponent, so we get t to the negative 1/2. Okay, that is 6t minus 2 over 1 over square root of t. I'm going to multiply top and bottom by the square root of t, which is the same thing as multiplying by that reciprocal on the bottom. And we get 6t to the 3/2, add your powers, we're multiplying t's together, minus 2 square root of t. Okay, could also write that as t to the 1/2, that's fine too. So that is dy dx. We can find the slope at any time t using this formula. Next we're going to find the second derivative. So the second derivative, I'm going to say what it is the first derivative, or is the derivative with respect to x of the first derivative. Okay? Usually everybody is great with me right there. Okay, now that means we have the derivative with respect to x of dy dx, which is what we just found. 6t to the 3/2 minus 2t, and I'm going to write that as t to the 1/2 since we're about to take the derivative. Okay, we are taking the derivative of this with respect to x, so we have to use implicit differentiation. So this is, first we take the derivative with respect to t, and then we multiply by dt dx. That's how you take we do implicit differentiation. So 3/2 times 6 is going to be 9t to the 1/2, because 3/2 times 6 is 9, minus 1/2 times 2 is 1, t to the negative 1/2 again. That's the derivative with respect to t, and now we're going to multiply by dt dx since we're taking the derivative with respect to x. All right, we're not done yet. We need to do something with this guy. We need to get an expression for dt dx. We don't know what dt dx is. We don't know what that is, but we do know what dx dt is. We were given what dx dt is. Dx dt is well, we weren't given what it is, but we know what it is. Dx dt is 2t to the 1/2 power, right? So that is dx dt. Oh my goodness, no. Dx dt is not that. That's just x. Dx dt is t to the negative 1/2 power, which is 1 over square root of t. Oh, okay. So that's dx dt. If dx dt is 1 over square root of t, then what is dut dx? Well, dt dx is just the reciprocal of that, so dt dx is just the square root of t. So this is 9 times t to the 1/2, which is square root of t, minus 1 over square root of t times the square root of t. That would be a safe stop spot. 9 square root of t times square root of t is 9t. 1 over square root of t times square root of t is 1. So the second derivative of y with respect to x is 9t minus 1. Okay? We'll do another one. It's all right. Okay. Next up, given the parametric equations, so we have x is equal to 4 cosine t and y is equal to 3 sine t. We are to write an equation of the line tangent to the curve at the point when t is 3 pi over 4. Well, slope of the line, or equation of the line tangent, I know that I need point and slope. Right? So first I'm going to find the point, then I'll find the slope. So the point when time is 3 pi over 4, we need the x-coordinate and the y-coordinate. So the x-coordinate will be 4 cosine of 3 pi over 4. Cosine of 3 pi over 4 is going to be a negative square root of 2 over 2, little unit circle value. So negative 2 square root of 2. The y-coordinate will be 3 sine of 3 pi over 4. That'll be 3 times positive square root of 2 over 2. So 3 square root of 2 over 2. Second quadrant, right? Slope. The slope will be dy dx when time is 3 pi over 4. So I'm going to take y prime and divide it by x prime, and then I'm going to plug in 3 pi over 4 for time. So y prime dy dt is going to be 3 cosine of t, and x prime dx dt is going to be 4 times a negative sine of t. And now it's time to plug in 3 pi over 4 for t. This will give us 3 cosine of 3 pi over 4 is negative square root of 2 over 2. And then we have negative 4 sine of 3 pi over 4 is positive square root of 2 over 2. Okay. So let's see, the square root of 2 is over 2 will cancel out, the negatives cancel out, and we have 3 over 4 is the slope. So the equation of the line tangent will be y minus the y value is equal to the slope times x minus the x value. It's the equation of the line tangent. Okay. All right. Number 3. Okay, we have a new x and a new y here. X is this and y is this. Find all points of horizontal tangency. So first of all, we're finding points. So my answer needs to be a point. Horizontal tangency. Okay, horizontal tangent is when the slope, so horizontal tangent is when the slope, dy dx, is equal to 0. What will make dy, so dy dx is y prime over x prime, right? So what will make the slope 0? The slope will be 0 when y prime, which is dy dt, is 0. For vertical tangency, it'll be the other way around, right? So we need to find dy dt, set it equal to 0, and get that time. So dy dt is 2t minus 3, which is 0 when t is 3/2. Okay? So we know the time when we have a horizontal tangency. We need the points. So we need x at that value and y at that value of time. So x at 3/2 will be 9/4 plus 3/2. We're going to have some fun with fractions here. Our common denominator is a 4. 9 plus, we need to multiply the 3 times a 2, because we multiplied the 2 times 2. So 15/4 is the x-coordinate of the point. Y at 3/2 will be 9/4 minus 3 times 3/2 plus 5. More fun with fractions. Common denominator is 4 again. We have 9. This would be minus 9 times 2 and this would be a 20 to get that 5. So let's see, we have positive 2 plus 9 is 11/4, so the y-coordinate is 11/4. So the horizontal tangent is at the point 15/4, 11/4. So at the end of your problem, write your answer. Okay? All right, vertical tangency. So to have a vertical tangent, that's when dy dx is undefined. And dy dx will be undefined when the denominator is 0, and our denominator is dx dt. Okay, it all makes sense. Everything from what you used to do back in Algebra 1 with vertical slope. Vertical slope is when the slope is undefined. No, I'm sorry, vertical line. A vertical line is when the slope is undefined. So we want dx dt to be 0. dx dt is 2t minus 1. Little power rule. So we get time as 1/2. Again, we want the points. So we're going to find x at 1/2 and y at 1/2. So x at 1/2 is going to be 1/4 plus 1/2, which is 3/4. I can do that one in my head. Y at 1/2 will be 1/4 minus 3/2 plus 5. Can't do that one in my head. Common denominator time. We have 1/4 minus 6/4 plus 20/4. So let's see. I think that's, oh my, that's going to be 14 plus 1 is 15/4. Okay. So the vertical tangent is at the point 3/4, 15/4. Oh goodness, and I can see that I made a mistake here. I just took a glance at my key and it looks like I made a mistake and I'm trying to see what it was. Okay, I see what it was. This was supposed to be a plus here. Darn it. So the time is negative, not positive. T is negative 1/2. So I'm putting a negative 1/2 in for x, which will make that a minus right there. So instead of being 3/4, I'm going to have a negative 1/4. And here, this will be still be 1/4, and then this will be a positive 3/2. So they're all positive. So that's going to be a 27/4. So the point is negative 1/4, 27/4. Oh, one little mistake can just ruin the whole thing, of course. Okay, next up, our last example. Example 4 has 3 parts to it. Be like an FRQ. Okay, a particle is traveling in such a way so that dx dt is 1 over t plus 2. dy dt is 4t. So they didn't give us x and y, they gave us dx dt and dy dt. They do restrict time to be greater than or equal to 0. Okay? And then they tell us that when the time is 0, the particle is at the position ln of 3, 2. Okay? All right. Part A, what is the position of the particle at time 2? Well, if I have the position at time 0, that's my initial condition, my initial point. If I have the point at time 0, I can get the point at any other time if I know the velocity, and I do. So I can get this using the fundamental theorem. So I'm going to set up the fundamental theorem for both the x-coordinate and the y-coordinate, because if we want the position, we want both the x-coordinate and the y-coordinate. So the x-coordinate at time 2 minus the x-coordinate at time 0 is the integral from 0 to 2 of x prime. Fundamental theorem, right? It's been a little while since we used the fundamental theorem. We're going to be using it a little bit more this unit. All right, so we're looking for x of 2. We know that x of 0 is ln of 3. And we know that x prime is dx dt, which is 1 over t plus 2. Okay. Little integrating here. So the antiderivative of 1 over t plus 2 is natural log absolute value t plus 2. And we are going to evaluate that from 0 to 2. So this will be ln of 4 minus ln of 2. So x of 2, let me see how I wrote my answer over here, is ln of 4 minus ln of 2 plus ln of 3, right? So now it's a matter of, that would be a safe stop spot. There's nothing wrong with that. But we can clean that up a little bit using our log properties if we have a multiple choice answer. So this would be ln of 4 times 3 divided by 2, which is ln of 6. Definitely would be the multiple choice answer compared to this answer, right? So that's the x coordinate of our position when the time is 2. Now we're going to find the y coordinate of the position when the time is 2. So set up fundamental theorem for y. Okay, we know the y coordinate at time 0 is 2, and we know what y prime is, dy dt. All right, antiderivative of 4t is 2t squared. We're going to evaluate that from 0 to 2. So this will be 8 minus 0. So y at 2 is 10. So at time 2, the particle is at the point natural log of 6, 10. All right, part B. What is the average rate of change of y with respect to x? Average rate of change as t changes from 0 to 2. Look at part C. What is the instantaneous rate of change of y with respect to x? Exactly at time 1. Okay? Instant rate of change is derivative. It's the slope at that point. Average rate of change is not the derivative. Average rate of change is the slope between those 2 points. It's the average rate of change, so it's the slope. It's our old, I think of this as AROC. AROC. Just change in y over change in x. That's all it is. Okay? So our old Algebra 1 slope. So I'm going to write this as y at 2 minus y at 0 divided by x at 2 minus x at 0. Go back to my purple. Okay, y at 2, so I'm going to my y equation. Y at 2 will be 4 times 2. Y at 0 is 4 times 0. Oh, my goodness. Y at 2 is not 8. And y at 0 is not 0. Y at 2 we just found. Y at 2 was 10. Y at 0 we were given is 2. I was using my dy dt instead of my y's. Okay. X at 2 we just found is natural log of 6. And x at 0 we were given is natural log of 3. Okay. Okay, so this is 8 divided by ln of 6 divided by 3, which is 8 divided by ln of 2. This would be a safe stop spot. This would be the multiple choice answer. Okay, instant rate of change. Instant rate of change is dy dx. We want to find the instant rate of change at time 1. So this is dy dt divided by dx dt, both at time 1. dy dt was given to us as 4t. dx dt is given to us as 1 over t plus 2. We just need to put in 1 for t. This is going to be 4 multiplied top and bottom by 3. So this is 12 over 1, or just 12. Okay, so that is the basics, day 1 of parametrics. We only dealt with dy dx, the second derivative, and finding a point given the dx dt and dy dt. Tomorrow we go on to more fun.